Hi, welcome to this session titled Discerning Signal from Artifact, Current Issues and Future Directions in Resting State fMRI Quality Control. My co-organizer, Dr. Ali Golestani, and myself would like to thank the program committee and the reviewers for choosing our symposium proposal. So despite the widespread adoption of resting state fMRI and functional connectivity, its meaningful interpretation is hampered by a lack of understanding of its biophysical mechanisms and noise sources. Appropriate quality control, or QC, depends on an accurate understanding of potential sources of noise and artifacts, which has yet to be achieved. In this symposium, we aim to elicit insight on these topics from a group of international experts, and they include Dr. Daniel Rowe from Marquette University, who will speak to the implications of expanding the use of simultaneous multi-slice imaging acquisitions, Dr. Benedikt from Maastricht University, who will speak to the role of multi-echo acquisitions and their recommended adoption for improving fMRI data quality. Dr. Rasmus Birn from the University of Wisconsin, who will speak to the influence of motion and physiological artifacts and how they interact in terms of QC issues. And finally, I will speak about potential rethinking of QC standards for resting state fMRI in light of this new research into the neuronal significance of low frequency physiological signals in particular. We believe this knowledge is imperative to this rapidly developing field and will be critical to avoiding false findings.
In this talk, I'll be discussing the influence of motion and physiological noise on fMRI, quality control, the latest solutions, and ongoing challenges. In terms of conflicts of interest to declare, I'm a consultant for NOUS Imaging. I'm going to be focusing particularly on resting state functional connectivity because this technique is particularly sensitive to both motion and physiological noise. Now, functional connectivity in MRI we define as the correlation between time series. That is, if the signal fluctuates in synchrony between two or more brain regions, we call these areas to be functionally connected. Now, in addition to correlated neuronal activity, there's a lot of other reasons why the signal might have correlated fluctuations in two or more brain regions. For example, physiological noise, such as the heartbeat and respiration, head motion, or scanner instabilities. Now, first, the problem of head motion. This problem has been known about in the field of fMRI since the very beginning. However, about 3 studies in 2012 really highlighted what a problem this is for functional connectivity. In a study from Van Dyke and colleagues, they found that with increasing amounts of motion, the temporal signal-to-noise ratio decreased. This by itself is not really surprising. However, note the scale on that axis. Even very small amounts of movement from one frame to the next of less than 0.2 millimeters can significantly affect the functional connectivity. In a study from Power and colleagues, when they censored or scrubbed or threw out the time points large with motion from one frame to the next larger than 0.2 millimeters, they found significant differences in the connectivity maps. They also noted differences in terms of the distance dependence, that is, for long-range connections were differently affected than short-range connections. This distance dependence was also shown and noted by Satterthwaite and colleague, in this case looking not at the difference between censored and uncensored frames, but rather looking at the correlation between motion and the functional connectivity. This was particularly concerning because a similar distance dependence had been previously observed across development, that is, between kids and adults. Physiological noise can also cause problems. In particular, the pulsatile movement of the blood can cause signal changes, particularly in arteries and vessels, such as the circle of Willis that you see here. And the chest movements during respiration can cause beziero field changes that can result in a shift of the image in the phase encoding direction and therefore apparent motion. In addition, naturally during rest, the breathing varies in depth and in rate, and these changes can cause differences in the arterial CO2 levels, which can cause changes throughout the brain because CO2 is a very potent vasodilator. This was noted first by Richard Wise in 2004, and you can see very similar looking changes if you look not just at the end-tidal CO2, but at the envelope of the respiration volume per time. You see very similar looking signal changes. Now, what quality control metrics can we use to look at the quality of our data? One very useful one is the temporal signal-to-noise ratio, and that's really just the mean of the signal over time divided by its standard deviation over time. And this can be very useful for spotting some very gross abnormalities, such as this coil artifact here, where we had a loose connection in one of the elements of the coil, resulting in a decrease in the temporal signal to noise ratio. Another useful way to look at the quality of the data is using these carpet plots or gray plots. And in this case, the image is essentially unraveled and all of the voxels are one column and time is along the x-axis. And as you can note here with these dark bands, these are reflecting time points at which the majority of the voxels are showing a signal decrease, likely indicating some sort of artifact like motion or respiration. There's a couple of other quality control metrics that are useful. One is the frame-wise displacement. That is, given a 6 realignment parameters, you can calculate either the sum of the absolute values of those from one time point to the next, or the square root of the sum of the squares of these displacements. This frame-wise displacement can then be used to decide which time frames to ignore or censor in any further analyses. Another useful measure is what's called DVARS, which stands for the temporal derivative, then RMS variance over elements. And in this technique, basically, you're taking the difference in the image, in the actual signal from one time point to the next, squaring that, and then calculating the sum of that over the entire brain, and the square root of that. Another metric that's useful to look at would be the what we call QCFC. That is, it's the correlation between the quality control metrics, such as the mean frame-wise displacement and the functional connectivity. So as you can see here in this connectivity matrix or in the histograms of that correlation, you can see that when you apply censoring, the correlation between the mean frame-wise displacement and functional connectivity becomes closer to 0. It's also useful sometimes to look at the distance dependence of this particular QCFC metric and look at that relative to the distance as I've shown here. Other useful metrics are the network identifiability, such as the modularity, or the prediction and classification performance. For example, being able to detect the difference between patients and controls. Now, how can we correct for these sources of noise? Well, as anybody who's done functional MRI knows, there's a lot of different pre-processing steps. I'm just going to be focusing on a few that are particularly relevant for functional connectivity. In terms of physiological noise, there's a lot of tools out there to try to correct for physiological noise, and it's a growing field. So I'm not going to go into any of these in great detail, but perhaps you're able to pause the video and if you're interested in following up on these in more detail. In terms of correcting for motion, in addition to registering the images, it's often useful to censor out the high motion time points. You can identify them from a frame-wise displacement and then either remove these or interpolate values from the neighboring good time points. An equivalent way of generating this is to create a spike regressor for each time point sensor and then to remove them in a multiple linear regression framework. So there's a few other nuisance regressors that are useful to include, such as the motion realignment parameters and their derivatives, potentially the squares of these to account for some nonlinear effects. In addition, it's useful to include the average white matter and CSF and potentially the global signal as well as their derivatives. And this is particularly helpful in removing some of the respiration volume per time related signal changes. A variation of that is to regress out the local white matter around each voxel, a technique that's called anatochore. And another variant as well is, instead of calculating the mean white matter and CSF and removing those, is to use the first few principal components of the voxels within the white matter and CSF, a technique known as CompCore that's also been shown to be quite effective. I just want to highlight a couple from my own lab. Generally, motion occurs most prominently at the edges of the image and therefore at the edges of the brain, and therefore you can use that information, the principal components of that, for some denoising. And also, we've come up with a more accurate model of the motion-induced signal changes that can more accurately represent the motion-related signal changes and therefore remove those, a technique that we call ModeSim. Finally, there are some data-driven approaches to clean up the data. The basic idea behind all of these is to perform a spatial ICA and then to classify these components as either noise and signal and then remove the noise components. A few issues I wanted to touch on. One that comes up repeatedly is the question of global signal regression. That is, should you regress out the global signal over the whole brain or not? As studies have shown, if you apply global signal regression, you do reduce the correlation with areas that are not expected to be connected, such as this widespread gray matter correlation that you see at the bottom left. In addition, we've shown that the correlation between the respiration volume per time changes is correlated with this global signal. And studies have also shown that motion-related signal changes can be reduced using global signal regression. However, the global signal by definition also contains the signals of interest, and therefore there's a possibility, as some people have raised, of distorting either individual or even group level results by including this global signal regression step. Perhaps the best way to reframe this debate about whether or not to do global signal regression is to focus more closely on what this global signal really is. Is it mostly noise that we can then therefore get rid of, or does it contain enough signals of interest that if we were to remove them from the data would really distort our results? This global signal regression has also been shown to increase the distance dependence. However, as was pointed out by Satterthwaite and colleagues, this is actually due not because global signal regression is introducing motion dependence, but rather because it is differently effective at denoising long versus short range connections. Another limitation to be aware of with this QCFC metric is that reducing the correlation with motion across subjects does not necessarily imply improved image quality. For example, if I were simply to add a lot of noise to my data, I would reduce the correlation with motion, but most people would agree that that's not the desired outcome. So other important thing to keep in mind is that the motion has been shown to be correlated with individual differences in traits, so actual neural differences. One other thing that's been found is that these FD measures, keep in mind that these can be affected by respiration. As I pointed out earlier, the respiration, the movement of the chest wall, can cause changes in the magnetic field that shifts the image in the phase encoding direction. This can actually be very easily corrected because there's no through plane movement here. However, if you were to use these FD measures to decide on which image time points to remove, you might be unnecessarily removing a lot of time points that were actually successfully corrected. And finally, I think it's useful to keep in mind the degrees of freedom, and that is censoring and bandpass filtering both can significantly reduce degrees of freedom. So in general, it's best to acquire lots of data using long time series or multiple runs, but unfortunately that's not always practical, particularly for pediatric studies or for patients. And so you have to really balance and weigh the amount of signal cleanup you can do versus how many participants you're able to include in the study. So in conclusion, I hope I've shown that the motion and physiological noise are significant sources of noise, particularly for resting state functional connectivity, and should be corrected. I would also emphasize to please look at your data and evaluate these quality control metrics, and of course be aware of some of these limitations of the quality control metrics. Thank you very much.
Okay, hi. So thanks for this opportunity to present my talk on multi-echo acquisition for fMRI sensitivity enhancement and data quality control, which is part of the symposium organized by Chen and Ali Golestani. And I'm Benedikt Poser from Maastricht University, and feel free to contact me afterwards if you have any questions. To just start off with a quick overview, at the risk of boring some of you, I will revise how the signal decay upon volt activation works. I think this is very important for understanding the motivations for multi-echo sampling. I will also go through how multi-echo sampling differs from single echo sampling, and then devote the majority of the talk to going into the reasons for why you want to do multi-echo. So first and foremost, for increasing volt sensitivity, but this can come in different flavors or forms, for instance, by actually going into the separation of S0 and T2 star, using denoising techniques like the ICA or Tadana, which I will spend quite a bit of time on. And then I will round off with some practical aspects relating to the sampling and its trade-offs. Now, the fMRI signal depends on T2 star. This is why it's called the blood oxygenation level dependent signal. And what happens is that during activation, when the oxygenation level goes up, your signal decay will be somewhat slower than in the resting condition. So you have this slight difference between those two decay curves. It will follow a simple exponential decay. What happens in a regular single echo EPI sequence is that you have an RF pulse to excite the signal from one slice, and then you place an EPI readout at some reasonable choice of echo time, and the duration of this readout will depend on your matrix size, so the spatial resolution that you require. There is really not all that much to doing multi-echo. Again, you excite a signal using an RF pulse, but instead now of having a single echo readout, you have a rapid concatenation of, say, 3 to 5 now undersampled readouts in order to sample this decay curve at multiple times in a single shot. Now you have to use parallel imaging undersampling in order to get each of these readouts short enough to be able to put many of them together in concatenation. So what this looks like in practice is you excite the signal of one slice and immediately get 5 echoes, excite the next slice, 5 echoes, next slice, 5 echoes, next slice, 5 echoes, next slice, 5 echoes. Now, this is all very well, but it actually gives you a pretty long TR, like in the regular 2D EPI sequence. Luckily, you can also add some SMS or multiband into the game. For instance, if you have a multiband factor of 2, you can excite 2 slices at once and get all the echoes for those 2 slices, and next, and next. And you see, using multiband factor of 2, you have already halved your TR as in a regular multiband acquisition. You can also play this for multiband 3. In this case, for the 12 slices, you can get them in only 2 shots, and correspondingly, your TR would be even shorter. This is some example data here from a 3 Tesla scanner at a fairly moderate resolution here, 5 echoes at a fairly reasonable range of echo times. So those were acquired with grappa 3 in plane and multiband factor 3 in order to reduce the temporal, to increase the temporal resolution. Having said all this, I just briefly want to give a bit of a history of multi-echo acquisition. From what I see, it really started off with a paper by Oliver Speck in 1998, where he suggested using multi-echo sampling for the separation of T2 star and S0, and I will show some of that. Very little later, Stefan Posse showed that multi-echo EPI can also be used to increase bolt sensitivity by combining the echoes together in some smarter ways. Again, a few years later, by work by myself and later others, performed the same thing again at 3 Tesla, again showing the gains in bolt sensitivity from doing multi-echo. You can push further in field strength, and even at 7 Tesla, we found that multi-echo EPI is beneficial. However, you will then find that you are pretty much limited in the spatial resolutions you can play out, bearing in mind that especially at high field, we typically want to go fast, go at very high resolution. Now, multi-echo is used quite widely for fMRI denoising, but also for simultaneous acquisitions of ASL and bolt, for example. More recently, and this, in my view, is a very big step, is the combination of multi-echo and multiband, which has really put multi-echo back into the game again and made it very competitive, since for a while, the multiband had really taken over the field and people just wanted to go fast and threw away the idea of doing multi-echo sampling. But now the combination of the two is really super competitive. And I think there's a good place for multi-echo EPI to be used routinely. And that is a point I'm trying to make here. Okay, so what are the motivations for doing it? I've indicated that multi-echo EPI can be used for increasing bolt sensitivity. It gives us multiple measurements of the bolt signal at different echo times in one shot and at literally no cost, and allows you to recover the signal that's lost due to dropout. It allows you also to separate T2 star and S0 effects, which is nice because T2 star is the more direct measure of bolt, and S0 is typically associated with motion, pulsation, scanner instability, etc. And there are a bunch of special applications that I will not go into today, such as dynamic distortion correction or special studies that look at the hemodynamic response and how it works. Okay, so first and foremost, motivation is that single echo fMRI is always a compromise. Now, I've explained the difference in signal decay between activation and rest, and you have to make a choice of echo time, which should ideally be dictated by what the value or the predominant value of your T2 star and the gray matter tissue is. So you want to sample at this point where the difference between activation and rest is the greatest. And if you plot this difference, you will get this bell-shaped curve here. You can also measure this experimentally, as done by Stefan Posse many, many years ago at 1.5 Tesla using a visual stimulus. And you can actually see that this peak very clearly aligns with the predominant T2 star of 70 milliseconds. Now, the problem is that T2 star varies across the brain, and it does so quite a lot. So while in some voxels you might be wanting to use an echo time like this, there are other regions of the brain where your T2 star or apparent T2 star is a lot shorter, and you would want to be using a shorter echo time. So there is no single optimum echo time that adequately covers your bolt response in the brain. Similarly, there are regions in the brain that are affected more strongly than others by signal loss or dropouts or signal voids, whatever you want to call them. And in particular, I'm talking about the regions here against the near the auditory canals or the frontal brain regions, where the signal dies off really, really rapidly, as you can see here from these 5 echo 3 Tesla data. So what happens is typically a very much shorter than optimal echo time is chosen, which means you're really sacrificing your sensitivity anywhere else to the point of the sensitivity dropping down to 60 or maybe 50% of what you would want to be at for the areas of the brain with a longer T2 star. Finally, as indicated, multi-echo gives you opportunity to separate task-related from artifactual signal changes, because the bold effects happen in T2 star, whereas the artifacts happen in S0, which is the signal at echo time 0, whereas the T2 star, as said, is the rate at which the signal then decays. So if you have a multi-echo acquisition, you can perform a fit to separate out the S0 and the T2 star. And for this visual stimulus here in the work by Oliver Speck many years ago, you see very nicely that the T2 star time course follows the visual activation, whereas the S0 would capture anything else, which is pulsation, motion, or slow drift, or heating in the scanner here in this case. So this works, and it's been shown very early on. But okay then, so we have a multi-echo sequence, we acquire some multi-echo data. What do we now do with this data in practice? Now, the easy way is just combine the echoes together in a more or less smart way. If you merge all the echoes into one time series, you have only one time series to deal with, and you can proceed with a standard analysis. So that sounds very handy. In principle, of course, nothing would stop you from performing separate fMRI analysis on each of the echo time courses separately, and then going in and picking the best Z-score or T-score for each of the voxels. Now, you can do that, but I think it doesn't take much to realize that this is suboptimal, because we should always exploit the benefits of signal averaging. So this is what we're going to look at here. Simplest thing in a way is to perform echo summation with equal weights. So you just take all the echoes as they come in from the scanner, you average them together or sum them together, and you will find that this improves sensitivity, at least up to a certain point. And this was simulated and shown again by very early work by Posse, that pretty much whatever you do, you will have some sensitivity gain that is in the positive. But if you start adding too many late echoes, you'll also find that the sensitivity will drop again because you start adding too much noise. In practice, you will not encounter this. In practice, summation is a perfectly valid way of doing it. I'm just pointing out that there is a risk of adding in noise for later echoes. What you really want to be doing then is have a weighted combination that is adaptive with voxel-wise weights. And you want to weight the echoes according to how much the echo times and pixels contribute to the bold sensitivity. So in practice, that means if you have a red voxel here in the frontal region where the signal decays fast and the bold sensitivity curves is weighted towards the shorter echo times, you want to give more weights to the shorter echoes, the early echoes. Whereas if you have a blue pixel, for example, which has a brain region of slow signal decay, you would also want to be putting more weight on the later echoes. So this is then some typical results you might get if you do this. Here's a single echo at a typical echo time of 30 milliseconds at 3 Tesla. You see again these sort of big holes around the auditory cortex in the frontal regions. And if you have a weighted summation of 5 echoes, you see how these areas are very nicely filled in with basically no dropout being visible here. In terms of the relative performance of these methods, this goes back to early work by myself at 3 Tesla here. We found that CNR weighting is best for task fMRI at 3 Tesla. By CNR weighting, I mean basically determining the temporal signal to noise of each echo in order to compute how much does each echo effectively contribute, and then weight the time series of the echoes accordingly. Result, in a nutshell, is basically that whatever you do, you will always win but never lose. But we found that CNR weighting is somewhat better than using a T2 star weighted approach or simply summing them together. So there's always a bit more gain if you do this GSNR based or CNR based weighting than the other choices. But the main point is you will always gain some. At 7 Tesla, it was a little simpler. Basically because all the echo times contribute similarly, at least for this experiment, which we performed at those echo times here. Similar sensitivity of each echo basically meant there was no additional benefit of having any fancy summation scheme, so just lumping them together into a simple sum was perfectly adequate. Okay, now having said all this, you might provocatively argue that echo weighting might have become redundant in some way given the availability of much more advanced multi-echo denoising options, for instance, the multi-echo ICA Tidana that I'm about to talk about. But this is actually not true for real-time applications like neurofeedback, for instance, where you very rapidly have to perform data analysis on the images that come in, compute your next feedback, and so on. So you don't really have time for anything too fancy, and your data must be maximally good. So here's a good case for optimizing your bold sensitivity in real time based on the data as they come in without doing anything fancy like this processing. Now, this is a slide here from Stefan Hoeneß, and this is actually his results shown at the Benedikt ISMR meeting last year. So he again looked at different ways of combining the echoes on the fly using a weighting by pre-scan T2 star or TSNR maps versus real-time computed T2 star. And again, very much in line with other work, he observed 20 to 100% sensitivity gain for all the methods compared to a typical echo time. Very nice. Okay, so there are smarter ways, though, than just combining the echoes together. And that is really exploiting what the echoes tell you. And that is a heck of a lot. And here I'm now talking about multi-echo ICA denoising and the time-dependent echo analysis, as was proposed by Prantik Kundu. Now, the echo time dependence of changes induced by T2 star or S0 is fundamentally different. Now, if we look at T2 star induced signal changes, so changes in the decay rate, and we look at the relative signal changes per echo time, we see this bell-shaped curve that I showed you earlier. Another interesting way to look at it, however, is to express this as a relative signal change, which is basically the delta S as a function of echo time over the signal as a function of echo time. And what you then observe is that you have a linear dependence of this relative signal change on echo time. So this is for changes in T2 star. This is not so for any signal changes induced by S0. You can go through the same game again, but you will end up seeing is you have a flat echo time dependence or no echo time dependence of any signal changes that happen in the S0 component. And this is effectively what Prantik showed in his work in 2011, and which is the key, or understanding which is the key for separating changes that are related to activation and changes that are related to nuisance, like drift, motion, and fluctuation. So again, coming back to this work by Oliver Speck here, the simplest thing you can do is then say, okay, well, we have the multi-echo data, we simply fit it, we separate T2 star and S0, we have a plot of what's probably signal changes due to drift and motion, pulsation, etc., and we get the T2 star courses, time courses as a representative metric for our activation. By the way, this also allows for doing triggered non-steady state fMRI. For instance, in brainstem, this might be advantageous using triggering when you're no longer in a steady state because your TR varies from shot to shot. And this was some work by Florian Weissner about 10 years ago. You can also do the T2 star calculation on multi-echo data now at higher field strength at 3 Tesla. Some examples are shown here, where compared different weighting schemes like CNR weighting, bold weighting versus fitted T2 star, and this also worked very well. Looking at the S0 components or signal components extracted by melodic, which have an S0 dependence, they mainly show artifact breathing and flow. You can basically see that by just eyeballing them here. And the question, of course, being asked, how are these components suitable filters for data cleaning? Well, of course they are. And coming back to the multi-echo denoising by Prantik Kundu again, this is exactly what's at the core of it. The way that he proposed for doing this was to spatially concatenate the echoes together, say 3 echoes in this case, and then perform an ICA to model the TE dependence of the component, or to extract components and then look at them to what extent they show a T2 star-like behavior or a change in S0-like behavior. So how this works is that he took the knowledge that the signal decay is pretty much mono-exponential. He combined it with the TE dependence model proposed by Harvey-Mann in 1994. And then you can arrive at two expressions that try to capture how the signal changes, either as a function of S0 or as a function of T2 star, R2 star, as a function of echo time. So you can obtain your components by doing the ICA on the concatenated echoes. And then for each of the components, you determine the goodness of fit to either this model or that model. And then you can get a measure of how bolt-like a component is. For instance, this component looks very bolt-like because it nicely shows the resting state network popping up. Or you can get a artifact-like component characterized by the Rowe, bolt-like is kappa, which looks very much like motion because you have this sort of activations around the skull. Okay, now how do you do this in practice? It's very well described in Pantik's paper, and I don't really have too much time to go into this here, but I do really want to point out that there has been a lot of work going on recently in making this method very accessible now. Originally, there were scripts provided by Pantik himself that were AVNI-based and really intertwined with AVNI and very hard to actually apply by anyone who wasn't familiar with AVNI. But the more recent effort of the Tedana community has been absolutely fabulous, and it's like super well documented. I've even gone into building a sort of a bits compliant pipeline, which people are able to download and use. Now, this really makes it accessible for everybody. It's open source, it's Python, it's extremely well documented, and it has a lot of background information, way more than I can capture in this talk here. And it has links to very useful resources as well, like other papers that have used multi-echo or protocols that you could use for examples. So with this, I should really give very big kudos to this Tedana community. And I highlight Elizabeth Dupré here, who's the BDFL of this project. And it's really amazing what they've put together in the last couple of years. Okay, getting closer to wrapping up, I want to go a little bit into the practical limitations. Now, multi-echo is at a free lunch. So far sounded like as though if it was, to a large degree it is. However, there are some limitations that you have to bear in mind, of course. Now, the first one is spatial resolution. The duration of each of the EPI readouts increases with the resolution linearly, but we also need to be able to sample the bolt response at reasonable echo times. So we can't just push this out endlessly and sample it like echo times. It would make our TR long, and it would also sacrifice our sensitivity. Now, looking at practical examples without going into the details of matrix size and bandwidth and so on, I would say if you have a sort of a resolution of 2.5 millimeter voxels at 3 Tesla, you can get 3 echoes, factor 2 in plane resolution. 3 millimeters, maybe you can get 4 echoes, 3.5 millimeters, so it's a bit unfancy, low resolution. You can probably squeeze 5 echoes easily with a bit more acceleration here. Similarly, consideration supply at 7 Tesla. Now, so this is for the spatial resolutions that you can squeeze in order to sample your echoes at a reasonable echo time. But what about temporal resolution? You do want to use some multiband in order to deal with temporal resolution. However, you have to bear in mind that your total acceleration capability of your RF call is limited to say like a combined multi-echo, like a combined grappa factor or sense factor and multiband factor, reaching no more than 8 or 9. 9 is already very pushy. I would even say 8 is already on the pushy side. Because you have to bear in mind that even multiband, it is just a form of parallel imaging. It's no magic involved there. It is equally limiting as your in-plane acceleration. So what does this mean in practice? For acquisitions that have a factor 2 in plane, that basically means you can push to multiband 4. If you have a factor 3 in plane, you are probably limited to multiband 2, maximally 3. And again, similar considerations apply at 7 Tesla, but then you're anyway more limited because you're not able to use anything close to the spatial resolutions most people want to be using at 7 Tesla these days. So think about that and be careful. don't be too pushy, but with those protocols here at 3 Tesla, you can get very nice protocols with a TR well below 1.5 seconds at a pretty decent resolution quite easily. To conclude with some final remarks, I would argue that multi-echo EPI by itself can improve your bolt sensitivity in the whole brain at effectively no cost. You can remove all the compromises of single echo fMRI, at least in the context of normal neuroscientific studies. You can even reduce your signal voids. You can even reduce the distortions, sort of as a byproduct of the fact that you have to do parallel imaging acceleration. So each readout becomes shorter, there's fewer distortions. And there are different ways of combining the echoes together. Most importantly, however, there's a very powerful way of processing and data cleaning offered by the Tidana approach. And in any case, even though you require multi-echo data, in the end, you end up with one single combined time series, which you can just put through standard analysis. So all the pre-processing can effectively be put in a black box that is well-tuned, and a regular user would not have to go through any additional trouble of using multi-echo EPI. The sampling is easily combined with any 2D or 3D EPI, multi-band EPI, or spiral sequences. I just want to say that for completeness here. But the typical case, of course, is to have a 2D multi-band EPI, which you now run in multi-echo mode. Now, the take-home message should remain, however, that with modern hardware, so the good scanners we have, the very high quality of Grappa Sense and multi-band parallel imaging that we have now available, and now not least the availability of really excellent open source tools, I really do not see a good reason for not using multi-echo at 3 Tesla for a typical neuroscience study. So with this, I would like to thank you for attention, and I really urge you to go to the website of the Tidana and look at the wonderful resources this team has put together. Thank you very much.
So my talk is titled, Is Physiological Noise Really Noise? Evolving QC Standards in Resting State fMRI. This may seem like a controversial question, but please hear me out. So as you've heard from previous talks, the main noise sources, I'm not talking about artifacts, but rather noise. A simplified understanding is that there's thermal noise, physiological noise, and motion. Motion can be in turn related to physiological noise, as you heard in the preceding talk. In this talk, I will focus on physiological categories. The category of noise will be specifically looking at the low frequency variant of physiological noise. So what do I mean by these? So high frequency physiological noise, you know well about. So cardiac pulsation, respiratory fluctuations, they affect the bolt signal through things like magnetic susceptibility, motion, pulsatile flow, and etc. We are focusing on three main low frequency variables: heart rate variability, or HRV, respiratory volume variability, or RVT, and arterial carbon dioxide, or CO2. So the influence of these have been well studied, and over the years we've produced, there's been a wealth of work looking at the spatial and temporal contributions of these signals to the bolt signal. And so there is definitely spatial overlap, as you can see on the left. So each color represents a different noise source, and they do have very distinct regions of influence as well, which is also highly subject dependent. So the contribution also varies by field strength. So as you can see, the influence is perhaps more substantial at higher fields, so elicits a bigger concern. So the current consensus regarding QC, when we try to denoise, what are we generally using as a marker of whether denoising is working? One is a very common one, test-retest reproducibility. So one metric of this could be the intraclass correlation coefficient. And we also have had spatial specificity being a marker. And it's generally assumed that physiological noise, as they don't have neural relationships, they should be removed. And we should also expect that the removal should bring about a quality improvement in terms of the QC targets. And so is that really the case? So Birn and colleagues in 2014 demonstrated that when we remove RVT effects, we actually do not improve test-retest reliability, reproducibility. And this was especially reproduced by work from my lab a few years later, showing that in some cases there really isn't any effect on test-retest reproducibility if we remove certain physiological noise. But this also depends on the exact type of noise being removed. And for example, HRV and RV and CO2 do seem to improve test-retest reproducibility, but not specificity. So then this paper from 2011 really brings this question together quite nicely, addressing directly the implications of removing physiological noise for resting state fMRI, and focusing on the role of the autonomic nervous system and how these seemingly noisy signals can actually be neuronally meaningful. And so very recent work from Chen and colleagues 2013 demonstrated that there is definitely evidence of functional involvement in the associations with HRV, and Yuan and colleagues in 2013 again were the first to show in resting state RVT also has a significant neuronal association. So we'll start with HRV then. HRV is rather, it's less controversial in this way because it is a well-established marker of autonomic nervous function. It's been found to be impaired in brain damage related to different EEG bands in the awake and sleeping states, and it co-varies with cognitive flexibility as well as functional connectivity in very specific brain regions. Key areas of interaction include the anterior cingulate cortex, the amygdala, and some certain brainstem nuclei. And so in the past literature over the past 13, 14 years or so, we've seen a pretty consistent spatial pattern of HRV influence on the resting state fMRI signal. So regions across these studies tend to include the posterior cingulate, medial frontal, superior parietal, occipital cortices, which are nodes of the default mode network, as well as the thalamus. So the HRV-EEG correlations, which have been reported multiple times, also indicate a fairly clear neural involvement. So in terms of the networks that are being related, so one can point to the salience network, for example, because of the anterior cingulate and amygdala involvement, and also different frequency bands of HRV are also differentially associated with cognition. So this is not a monolithic sort of signal. So now turning to RVT, so like I mentioned, Yuan and colleagues from James Berdukov's lab were the first to demonstrate resting state fMRI. There is a significant association between alpha band global field power and RVT. So they are showing this significant cross correlation here. And we are seeking to expand on this work. So in my lab, we're looking at using wavelet coherence to delineate the time dependence of this relationship. So as you know, physiological noise is non-stationary, so expect there to be time dependence. And so we have found such significant and time-dependent relationships in alpha, theta, and delta bands, and here shown for the alpha band. So this is definitely a intersubject variant relationship as well. So regions affected by RVT since Rasmus's first paper, there has also been consensus on that. So you can see we generally observe the visual cortex, superior and middle temporal gyrus, inferior frontal gyrus, and inferior parietal lobule to be affected, which also overlap with the default mode network. And since the demonstration of the EEG-RVT relationship to be arousal dependent, so apparently in the eyes closed state, the relationship is stronger. So this is very interesting to me, and definitely implies it might further implicate cognition. So networks there seems to be a widespread influence of RVT removal on functional connectivity. What I'm showing here is for the default mode network, but it seems to have spread across multiple networks as well. So CO2, this is a more recent finding. My lab has been focusing quite a lot on this, but so I was happy to see this paper in 2016 by Driver and colleagues demonstrating using MEG that natural fluctuations in arterial CO2, which can be tracked through end-tidal CO2, also influence neural oscillatory power and in the alpha, beta, delta, and gamma bands. So, so in the literature, it has been reported that increases in arterial CO2 tend to decrease the levels of arousal, they decrease alpha EEG power, and also cognitive abilities. So this is not new, but in terms of the spontaneous CO2 fluctuations, would these amount to an actual fluctuation in cognitive ability? That is unclear. So regions of influence of CO2, again, there have been a number of studies addressing this, and there is some potential overlap temporally and spatially between RVT and CO2 influences. And it's also been shown that CO2 fluctuations can mimic functional networks. This is work by Molly Bright and colleagues. So networks associated with CO2 fluctuations, again, like RVT, there is widespread association. So in the default mode, motor, and visual networks, we see that when we remove CO2 fluctuations, this is from our work from this year, we see a general decrease in functional connectivity in all three networks. So Driver and colleagues suggested that the CO2 fluctuations influence cortical excitability due to this relationship between extracellular adenosine concentration and pH. Of course, the effect of arousal on this relationship is still unknown. So it suffices to say that these are not as simple as they might seem. One more note is that if HRV has a functional or cognitive significance, then why not respiratory signals? After all, they are interconnected through sinus arrhythmia, and modulating respiration can lead to HRV changes. This others and ourselves, we've already shown, and HRV and respiration do share a spatial and temporal influence. So the above really question the practice of correcting these signals independently and each in turn as a sort of monolith, because there are different components of these signals which may be neural and non-neural. So for example, a recent paper 2014 from Firscheller and colleagues segregated the HRV into two groups depending on its influence on the both signal temporally. So this could be an inroad into dissecting the signal and further understanding its neural implications. Just to summarize for you, we found that physiological noise removal actually reduces test-retest functional connectivity reproducibility. And so we also showed that there's evidence these signals are not entirely noise and may play meaningful roles in brain networks. So should test-retest reliability remain a main QC target? Based on this evidence, there might be questions about this practice. And while clinical translation often requires these measures to be reproducible, autonomic processes are by nature non-stationary. So how should we go forward? Perhaps one approach is to further dissect the signals into a neural component and a non-neural component before throwing the whole thing out. And another option is perhaps to embrace the non-stationary nature of functional connectivity. So I'd like to thank the individuals that contributed to this work from my lab, as well as from collaborating laboratories and my funding sources. And thank you for your time.